Good morning, ladies and gentlemen. This is Ben Keyser with Applied Flow Technology, and I would like to thank all of you for joining me today in our webinar talking about money talks, balancing initial and life cycle costs. And I'm excited to talk to all of you today. And I just want to let you know that if you are listening in live on today's webinar, there is a PDF copy of the slides that I've made available to you. And if you are listening into the recording, because the webinar is being recorded, feel free to email me directly at benkeyser@aft.com, and I will be happy to send you a copy of the slides as well. And my email is benkeiser@aft.com. All right. Before we get started, I just wanted to give a quick introduction to what we're talking about today. And so hopefully you are familiar with our website, aft.com. And under the products menu is where you can find more information about our software in the AFT software overview. And so on this page here, you can see our four primary products. There's AFT Fathom for liquid piping systems, steady state. AFT Aero models steady state for gas piping systems, takes into account all the compressible flow effects of a gas piping system. AFT Impulse models surge and water hammer and liquid piping systems. And then AFT Extreme is a brand new software tool that does gas hammer and steam hammer transients and gas piping system. And so each of the four primary products has a number of add-on modules that are available. And so for Fathom, there are four of them that are available. And what I'm going to be talking about later today is the automated network sizing module. And so the contents I will be demonstrating with AFT Fathom, but note that there's also a automated network sizing module for AFT Aero as well. And so when you see how the ANS module works with AFT Fathom, the ANS module for Aero works in the same fashion as far as the process goes for automatically sizing pipes. So if you want to know more information, this is where you can find it, aft.com under the products menu, and then AFT software overview, and then you can find more information about the automated network sizing module. All right, so let me go ahead and jump into this here. One of the things that kind of drives me nuts is seeing how there are so many people in this world that are going for energy efficiency and cleaner things, which is great, but they're looking in a lot of the wrong places. And so, there's nothing wrong at all with getting more energy efficient vehicles and doing your part to be able to try and, have a cleaner footprint, which is great. But the thing is, we're looking in all the wrong places. And so if you really want to make an impact, the thing that you should focus on is pump systems, because pump systems account for about 25% of the electrical motor energy usage consumption all around the world. And 20 to 60% of that electrical energy usage is in different types of industrial applications. And this is a study that comes out of the U.S. Industrial Motor Systems Opportunities Market Assessment done by the U.S. DOE through Oak Ridge National Labs. And they did a really useful breakdown here where it talks about the greatest electrical energy savings potential. And so the industries that have the greatest electrical savings potential is chemicals, paper products, oil and gas, rubber and plastics. And so these are the biggest industries where you can really make a big impact in making things more energy efficient. And the area where you can make them more efficient is in pump systems. And so, as you can see here, for pump systems, these are very, very energy intensive processes. And if you are able to find ways to make your pumps be more efficient so that there's not so much wasted energy, then there's going to be lots of money left over that you'd be able to invest in other types of energy efficient and other types of clean processing measures as well. And so, as you can see, upgrades to pump systems carries a big potential there. Compressed air systems. For doing motor upgrades, you can get some good increases in energy efficiency for that. But again, the biggest area to focus on is your pump systems. And thankfully, it's really not that difficult to where you can experience very large savings very quickly. And we're going to go into a few different ways that can be accomplished here today. One moment here. Sorry about that. Okay, so another case study here is in Finland. They did a another diagnostic analysis of almost 1,700 pumps in 20 different industrial process plants. And what they found was that the average pumping efficiency was below 40%. And get this, 10% of the pumps that they had studied were actually operating below 10% efficiency. Now, think about the outcomes of this. It's not just lots of wasted energy that they're losing. Think about where the pumps are operating at on their curves, where they are very far away from their best efficiency points. So it's not just causing wasted energy to happen, they're also going to be having to deal with constant pump repairs and product losses and things going wrong in the plant. And so, in order to ensure safe and clean operation, it is crucial for those pumps to be operating properly. And so, a few things that caused these pumps to operate so inefficiently was throttled valves, pumps being oversized. So, those are two of the biggest factors that led to all of these 1,700 pumps to operating very inefficiently. One of the other things that they found was that it caused lots of leaks to happen, and seal leakage caused the highest downtime and cost in these plants. And so this is going to have a very huge impact on your life cycle cost over the long run. Now, if we were to focus on one specific plant here, this is just a conventional 75 horsepower pumping system. And if we were to look at the costs over a 25-year life cycle, this is a good example of what you might see, where your initial cost here is a fairly small percentage of the overall pie. So for this particular system, $70,000 is what it costs to build the system, and to install it, another $61,000. So that's a very small piece of the pie right there, 17% of the overall cost. Maintenance was about 28%. And that makes sense, especially if they're operating far away from their best efficiency point. There's going to be a lot of repairs that they're going to have to deal with. And then finally, operating cost was 55% of the overall cost in the 20-year life cycle. So here, the operating and maintenance costs accounts for 83%. One of the most important costs that owner operators and EPC companies usually care about the most, it's the initial cost and the installation cost. And so those are the two primary drivers of new system designs. And as you saw in the previous slide, lots of throttled valves, lots of pump oversizing. So if operating costs and maintenance costs account for 80%, why do we care so much about installation and initial costs? Well, here's a few different reasons why that might be the case. One case is simply just lack of education on piping system operation in itself. Flow analysis is still a relatively new thing, in the whole history of engineering, and so there are a lot of useful tools now that can help engineers get a much better look at what's going on inside the entire system. And the thing is, when you have much better visibility, you are now seeing lots of different problems that you may never have seen before when you're looking at it at a deep level. And so flow analysis is really important to do to be able to uncover problems in operation, as well as opportunities to just allow operation to be better. Other reasons is simply budget constraints. The engineering companies are usually not stuck with the utility bill, and overall, there aren't any standards really that guide system design. I mean, yeah, there's rules of thumb out there, but as far as when it comes to flow analysis, companies are free to choose if they even do hydraulic calculations. Now, I obviously highly recommend that you do the hydraulic calculations and spend the time to do a flow analysis. A lot of people are still big believers in their spreadsheets. Well, spreadsheets are all good, but they make it very difficult to really see what's going on in the entire system in an efficient manner. So using a good flow analysis software tool is an excellent way to go. So let's say that we ignored the energy costs themselves. What things are important to consider? Well, if we look past the energy savings, we want to focus on safety. If you have a reliable process that's working properly, you can know that it's going to have much better safety out there in the plant. Higher reliability, things not breaking down as often. Increased productivity, you're not going to have as much downtime, less equipment wear and tear, less maintenance and repairs, less product losses. And so whenever you have downtime, you might have product losses, especially if there's a accident that happens in the system. You can use flow analysis software to help you get a much better capacity utilization in the plant, reduce the environmental impact, so that can help eliminate environmental fees if anything has been violated. And what does this all lead to? Better profitability. And so, if you look at energy savings, you're going to be focusing on how can you make the pumps operate better and more efficiently. When you're considering that, in general, you're also going to be looking at all these other things at the same time. And so just having awareness there is really important. All right, this is a case study that I like to talk about a lot. It's a case study of the Chrysler plant in Michigan in the United States where they make cars. And you can find a link to the case study itself. And one of the reasons why I really like this example is because the model here is very simplified. With a very simplified model, they were able to focus primarily on their pump operation. And after making various adjustments on their pump operation, they're able to save $194,000 a year in energy costs. And they're also awarded a $200,000 rebate from their local energy utility. So this is a great case study to show that you can accomplish big things with a very simple flow model. And this is only with focusing on the energy cost itself. This isn't considering, what it is to install a system or build a system that's brand new, only the energy cost itself. And one of the ways that they were able to make their system very simplified is they took their entire plant and they basically lumped it into this box right here with what we call a resistance curve, where you have pressure drop data versus flow. And ultimately, they had measured data where if this is the pressure drop and this is the flow, this is basically the type of data that they had, where you're going to see that quadratic pressure loss shape in the system. And so by lumping this data right into that little black box right there, that was able to completely account for all their system hydraulics. So you can still do great things with a very simple model. All right, so why do we want to focus on the pumping systems for improving energy efficiency? Because the pumps are highly influenced by the system. And so, yes, there are measures that you can take to increase pump efficiency in itself. But if you focus on the entire system as a whole, that's going to give you much better results. And so, if you are in a situation where you already have an existing system, flow analysis can be really helpful to find better ways to operate your system. And the case study for that was the Chrysler plant that I had demonstrated, because that was an existing system. But if you were to focus on designing a system that can operate more efficiently and more reliably from the design point of view, then you're going to be able to have much better impacts in the long run. So let's talk a little bit about concepts relating to design versus analysis. Uh, Designing a single component is not really the greatest approach to take, because you can only design it for specific conditions, and it makes it really difficult to see how it's going to impact the rest of the system. And so this is if you're just designing a heat exchanger or a pump or a valve. Certainly it is important to make sure that you know all the ins and outs of what is going on with those particular components, but it's also good practice to see how that's going to impact your system as a whole. When you focus on designing a complete system, you can better account for component interactions. It can reveal where you might have issues in places that are not obvious. You can find ways to optimize your system. And so we're going to see some examples of what that looks like here today when I go into a couple of models here. And so when you approach a system as a whole, it's going to help you uncover things that are not apparent if you're only looking at things piece by piece. When you're designing a new system, you can improve your efficiency and save money without having to do real world testing. So there's a major advantage to that. You can incorporate potential future modifications, so that way you can size your pumps for larger capacity later down the road, and your pipes would also be sized appropriately to be able to handle that. That can help you easily account for process changes, expansions, different things like that. And then finally, analysis comes into play a lot more for modeling existing systems, where some of the tasks you might be trying to do is eliminating cavitation and bottlenecks, minimizing repair costs and maintenance. How would you do that? Well, just by examining where your pumps are operating on the curves. And so if your pumps are operating far from their best efficiency points, then that's going to be a big indicator that you're probably going to be dealing with lots of pump repair issues. It can also help you increase the amount of time between failures, maximize uptime and profitability, and of course, efficiency. Now, let's talk about the differences between design versus analysis. And so if we consider AFT Fathom and AFT Impulse AFT Arrow, they are analysis tools. And so what do we mean by analysis? Give me 1 second. By analysis, we mean that your input is going to be the pipe size, pump data, your fittings and losses, your resistance curves, different things like that. And the results that you're going to see is flow rates, pressures, velocities, MPSH, valve open percentages, different things like that. And so that's what you're looking at as an analysis tool. Now, design is the opposite. For design, you know what your flow requirements or velocity requirements are, or what pressures that you might need in specific areas. So in that case, the output that you're going to be getting is what the pipe sizes are and what pumps you need in order to make those accommodations. So it's the opposite of analysis. So here, standard Fathom and Arrow, so F for Fathom, A for Arrow, these are analysis tools. Now, if you were to look at the ANS module for Fathom and Arrow, the ANS module is what you would be using for design purposes. Because with the ANS module, you're going to be specifying what your flow requirements are, your velocities, your pressures, all the things that you need. And then the ANS module will automatically determine what pipe sizes you need and pumps, different things like that. And so it's a very efficient way of being able to help you with your design that you'll see here in just a moment. So traditionally, the way that you would design a system with an analysis tool like AFT Fathom and AFT Arrow is through iteration. So you would specify a system where you're essentially guessing at all of your pipe sizes throughout the system. You run your model, you analyze your results, and then you make changes, and then you rerun your model. And you do that over and over and over again until you are meeting your design requirements. And so basically, analysis really is a sub-process of the design. And engineering rules of thumb can help provide guidance towards good system designs, but there's some issues here. So trying to find the best design with these types of methods is really difficult when you have so many different variables that you're dealing with, so many different pipe sizes that you might use, different pump curves. And when all those things interact with each other, especially if you've got control valves in the system, it can make trying to find the best combination of pipe sizes that result in a low cost headache. And the problem is that no one has time to go through that process to really look at all sorts of different options for design here. And that makes it really difficult to test allowing rules of thumb. What if you have a velocity requirement for 10 feet per second, but if you allow up to 12 feet per second, what if you're able to establish a bit better of a design that might save you a little bit more money? That's the issue, is that no one has enough time to be able to go through this process. And so this is where we're going to take a look at how the automated network sizing module can assist you. And this is a example of a cooling loop system that we're going to look at. But before I jump into that example, I want to talk about cost calculations really quick. So let me pull up my Fathom model here. By itself, AFT Fathom can do full system cost calculations. So this is a very basic example of maybe what a cooling tower network might look like. And so this just comes out of our standard examples. So if you have access to AFT Fathom, either the full version or even the demo version, you can open up this model and you can look at it. Where do you find it? Well, if you go to the help menu and you want to build this and you want to do the example, go down to show examples, pick your favorite units. And then the example that I'm demonstrating right here is the plant cooling cost calculation example. And so if you want to see how to do this example, you can just go right here and the tutorial will walk you through it. And so the key thing is, in this particular example, you're not actually building it from scratch. All of the other examples here in the tutorial, you build from scratch, but this particular one, you're starting with a completed model. Where do you find it? If you were to open up Fathom and go to the open for file open, typically where AFT software is installed is on your C drive, AFT products, AFT Fathom, and then examples. The model is called US, as in US units, plant cooling, and I'm looking at the completed version. If you want to start with the tutorial from the examples help file, it's this one that you would start with. This is the completed version where everything is done. And so as you go through the process of building in the cost information for pipe size, you've got your piping cost for dollar per foot based upon nominal size, and then your material and installation cost for your pumps and different things like that. There's a lot of cost information that's involved there. And so this example teaches you how to build those cost databases. So under analysis, if you go to cost settings, this is where you can see how to do the cost calculation. So I am calculating my costs. My energy cost that I'm using is 6 cents per kilowatt hour. And this example is going to calculate material, installation, and operating costs over a 10-year period. Now, this is an example where the pipes are already sized. So here, if you already know exactly what size you're going to need because the system has already been fully sized for you, then you can do one extra step nice and easily. And when you run the model, you can see what everything is going to cost. So here's the cost report that you can see for this example. And this particular system cost $3.2 million over a 10-year period. So the initial material and installation cost is $1.1 million, and that's pretty expensive. But look at this. In the long run, the energy cost just totally dominates. And so this is what we want to start considering with our designs is the energy cost. If you only focus on the initial cost itself and you try to drive that cost down, your energy cost is going to go up. The reason why is because if you're only focusing on material and installation costs and trying to drive that down, that's going to result in smaller pipe diameters, basically. Smaller pipe diameters are going to lead to higher pump requirements with higher horsepower because you have to overcome more pressure drop in the system. That's going to dramatically increase your operating cost there. So if we scroll down here, you can see all of the costs on a pipe by pipe basis. And so you can see the header costs. Those are the more expensive ones. $60,000 for material, $130,000 for installation. We also have our pump costs. So this is the material and installation for all pumps, each one listed individually. And then here's your operating cost, which is $522,000. And so that's where we have very significant energy costs in the long run. And then these are the costs of your fittings. And so these are all the elbows in the system and whatnot. You can account for those costs as well. So if you want to do cost calculations, you can do this already with standard AFT Fathom and AFT Arrow. Again, simply go to the help menu, show examples, pick your favorite units, and then you're going to find it in the cost calculation examples right here. Now, we don't just care about what the costs are. Being good engineers, we want to try and reduce those costs as much as we can. So I'm going to open up another example here. And so what we're going to deal with in this particular system is a brand new design. As you can see, I have 8-inch size for all of my pipes. Those are just initial guesses. I don't know what my pipe sizes are going to be, so that's where I'm starting. And so what I'm going to be doing is I'm going to use the automated network sizing module to size the pumps and the piping for two different scenarios. In one scenario, I'm only going to try and minimize the initial cost, and I'm going to see what the resulting sizes are. In the second scenario, I'm going to look at the entire life cycle cost, and I'm going to try and minimize that to see if I can save some money over the 20-year life cycle. So let me go ahead and open up that model here. All right. Okay, so here I built the model in the base scenario and I set up all my sizing parameters in this specific scenario. And so then what I did was I created these two additional scenarios right here. So let me go ahead and load the initial cost sizing scenario. First thing to do, in order to turn on the ANS module, once you have a license for it, is by clicking on the add-on modules button down in the bottom right corner of the interface. So if you have a license for the ANS module and you check the box, you'll just see that it stays checked. And so that means that you have checked out that add-on module. All right, so I've got the add-on module checked out. Once you check out that the add-on module, you're going to see a new sizing panel on, or a new sizing primary window on the 5 primary window tabs. So now there are 6. So when you're using the ANS module, there are 6 primary windows in that case. Now, quick thing here. You may be wondering, what in the world does this and sign mean? The ampersand. What this means is that for each of these pipes, I have included fittings and losses. And so I went through and I lumped in a number of elbows. So here there are 12 elbows that are standard 90-degree elbows. And so I have 12 elbows that I've lumped into that pipe. And so that's all that the ampersand sign means, is that you have lumped in additional fittings and losses into those pipes. If you look at the model data window, you can see, if you look in the piping section, that you have K factors. These represent those minor losses that I am including in the pipes. And so where you see larger K factor, this has the most elbows in it. If you look at the fittings and losses, you can get a better breakdown of the quantity of how many elbows there are. So the nice thing is you can account for these costs as well in your system. All right, so I've built the model of my piping system, and I don't know the pipe size. I also don't know the pump curve. So I'm trying to size my pump as well. So I've got 3,000 gallons per minute through each of my pumps, and I need to try and size my pipes. So here's what the process looks like. When I go to the sizing panel here, this is the first panel that you'll see. And so if I zoom in here, the first thing to do is to choose if you're going to size your pipes or if you're going to calculate the cost but not size them. This middle option here, this is just like the regular cost calculation capability of standard Fathom and Arrow. So that's what that option is. So if I chose that middle option, it's going to calculate what the system costs based upon the specified pipe diameters, which are 8 inches. And then finally, we have do not size. And so that option is going to be where it's just a regular Fathom run. So this option here is doing no cost. Why would you use this one? Well, if you've already gone through and you have specified all of the other panels down here, you're not going to want to have to go in and delete all that information if you just want to do a quick Fathom run. So you just click on this option. That way it saves you some time. All right, so we've gone through and we've specified that we're going to do a sizing calculation. The next thing is we're going to pick how we're going to size the system. Typically, you're going to use monetary cost. If you don't have any monetary cost information, you might do something like piping weight, because if you try to minimize your piping weight, that's usually going to track pretty well with minimizing your initial cost. But here, I have some cost information, which is pretty basic. And so I'm going to do monetary cost. Now, you don't have to have that much sophisticated pieces of information. All you really need is basically uh, information for your pipe sizes here. I have cost per unit of length for each of these different sizes. So basically, I have dollar per foot per size. This is all that you need for doing your piping cost. That's it. You don't have to have a really huge, sophisticated and accurate piece of information. The reason why is because even if this cost information is 10 years old, it doesn't matter. What you're trying to demonstrate is savings, okay? How much savings can I get if I try to minimize my material and installation cost compared to if I try to minimize my full 20-year life cycle cost instead? How much money can I save? So I've got my material and installation for pipes. I have my material and installation costs for my pumps. And then I have the material and installation cost for all of my elbows. So that's all that you need. It's pretty simple. So if you're wanting to be able to do this type of design and analysis approach, you don't have to get the most accurate pieces of information from your cost department. Just assuming a basic idea is perfectly fine. All right. So what we're doing here is for the options to minimize monetary cost, I have chosen the second option here. Size for initial cost, but show me what the energy costs are. So this is a great one to use because the energy cost, that is just simply an additional calculation that Fathom does for you. The only thing that you need to do, the only thing that you basically need to do is click on the for recurring costs for energy is the button that says cost report only. So I'm not trying to minimize the pipes for minimized life cycle cost. I just want to size based upon minimizing material and installation, but tell me what the associated energy costs are going to be for that. So that's nice and easy. So this is a system life of 20 years, and I'm going to look at a energy cost of 11 cents per kilowatt hour. So that's all that you really need to set up on the first panel here. It's pretty simple. That's all done. The next thing is to set up what's called your size and cost assignments. So here, if we break this down and take a look at it, we have the first half of the screen is sizing and cost options. So this is where you're going to choose which individual pipes you want to size or not size. Here, I want to size everything. So that's why I put everything in the always include in cost for automatically size. Now, I've already demonstrated how to do this in previous webinars, and so you can find these types of webinars in our webinar library. And let me do a quick aside to show you where you can find those really quick here. Let's see. So if you go to our website, aft.com, under the Learning Center, then webinars, and then webinar library, you just go in here and you fill out the information on the form. And then in AFT Fathom, there are several webinars where the ANS module has been demonstrated. And so let's see, here are some previous webinars where this has been demonstrated in more detail. How to size your pipes to meet different operating cases. That's one. Another one is, let's see, size your pipes in no time flat. This webinar discusses how you would be able to use the ANS module to size your pipes if you don't have any cost information. So you can, it will demonstrate how you would be able to use the ANS module to size your pipes based upon piping weight. And that way you can get a very quick sizing of a system. So this is definitely a good one to watch. Size your pipes in no time flat. And then let's see. Some other examples here is how to utilize the automated network sizing module, how to automate your pipe sizing calculations. And then this webinar right here, how much will your system cost you, is a great webinar because this teaches you how to build the cost databases which you're going to need for AFT Fathom. And I actually provided some links for you near the end of the presentation. And so you can find these links as well to some of those. So watch those webinars and it will go into more detail on how this panel is used. Ultimately, this is where you pick which pipes are going to be sized, which pumps are going to be sized, control valves, elbows, etc. And then the next thing that you're doing here is common size groups. So if I go back to my workspace here, and I just let the sizing tool do everything, I have 21 pipes on the workspace. It is possible that you might have 21 different pipe sizes in your system, and that's going to drive your purchasing team nuts. So there might be some areas where you want to ensure some commonality of pipe size. So maybe these two pipes have to be the same. Maybe these pipes right here in the pump area needs to be the same. Maybe these pipes need to be having some level of commonality. those are called common size groups. And I have already set that up in this example. There's a pressurizer, pump station, cooler piping, etc. And so if I go back to the workspace and I click on view and then color common size groups, this is how you can see which pipes are going to be in which common size group. And that way, these will all have their diameters changed during the sizing process, but they will end up with the same size in the end. After you set up your size groups, then you do your candidate sets. This is basically just where you specify which types of pipe materials are you allowed to use. And so here, I'm only considering one type of material and one type of schedule. So I'm only considering in this example standard schedules for pipes that are 1 inches to 36 inches in diameter. I'm not going to consider any pipe sizes outside of this range. You can if you want to, but in this particular case, I'm keeping it simple, just one candidate set, and then you would specify which common size group each candidate set goes with. And so this tells you that these groups of pipes can choose from within these types of materials. And it's going to automatically figure out what pipe size is needed based upon your design requirements. So here I have 3 design requirements for the pipes: maximum velocity, minimum pressure, and minimum flow. As you can see here, maximum velocity applies to everything, so does minimum pressure. But the minimum cooler flow only applies to one common size group. And so this is where you can do as many design requirements as you want, and you can have it apply to multiple groups. And what you're going to find is that maybe some of these requirements, they may not even matter in your overall design. You might say, hey, I want to make sure that all my pipes are above 15 psia. Well, you very well might find out that you didn't even need that design requirement in the first place, because the ultimate things that might drive your design is velocity and flow. And so this basically just figures out that for you. It'll tell you which design requirements matter and which ones don't. For my pumps, I have a MPSH margin that I want to make sure that I can meet. So I want at least 10 feet of margin on my MPSH. And then for my, and then that's it. So I've got 4 design requirements in this model. And then lastly, all of the costs have been set up. I'm not going to go over how to set up the cost databases in this webinar today. So please be sure to refer to those other webinars, and that way it'll demonstrate how to do that. And so last but not least was the sizing method. And this is what you would choose to allow the automated solver to figure out what the best combination of sizes is going to be. And so now I'm all ready, and I'm going to run the model. So what it's doing is it's running the model, and it is trying to find the best feasible cost for initial cost. It's trying to take this as low as it possibly can while meeting all of design requirements. And so this is basically going through all of those iterations for you. So it's changing pipe sizes for all those different flow paths, and then it's running it and it's looking at your design requirements, and then it keeps changing the pipe size over and over. And the total execution time, 32 seconds. So that's pretty good. 1 second. Okay, so most important thing, how much does everything cost? Well, based upon this sizing that we just did, it's going to be just over $4 million for this piping system. And so the material and installation, this is what we were trying to minimize. We were trying to establish as low of a minimum or as low of a material and installation cost as we could. So the total material and installation cost is $750,000. And so you can scroll down this list and see how the cost breakdown fits everything. And the vast majority of the cost in this system here is our operating cost. $3.3 million. That is massive, especially compared to $750,000. And so for $750,000, that is significant. That's basically 18% of the overall cost. And so I want you to remember that value. So remember $750,000 for the material and installation cost. And this is why I chose to do my energy cost calculation as well. It's not sizing my pipes based upon that. It's just calculating what the energy cost is, which is $3.3 million. And so 750 out of basically $4.05 million is roughly about 18%. Okay, so remember those three numbers: $750,000, 3.3 million for energy cost, and your initial costs are 18% of your total costs in the long run. Now you get to see what your pump requirements are. And so this gives you the breakdown of what your pump requirements are. And then if I look at my pipes, here is my design requirements. And you can see that these are the velocities that were most important because these are what drove the design for the most part. And here's the resulting pipe sizes that you need. So pipe sizes range between 10 inches to 20 inches in diameter in this scenario. And so if you remember on the sizing panel, what I did was I chose this second option. That way it sized my pipes based upon material and installation, but I clicked the radio button to still calculate a energy cost for me anyway. This is why the ANS module is so powerful and so useful, is because when I created my second scenario for doing the life cycle cost sizing, the only change I needed to make was instead of clicking on this button, I clicked on this button, which is this option right here, size for initial and recurring cost. So this is the only thing I needed to do was to choose this option. I didn't have to make any changes at all to any of these other panels. So literally, by the click of one button, after I ran my model, it took 6 seconds to run this model. And here's our costs. We took it down from $4.05 million down to $3.34 million. So that's a pretty significant reduction. Okay. I'm just doing a quick calculation there. So that saved us about 21% of the overall cost in the system. Now, the initial non-recurring subtotal, that went from $750,000 to about $1.1 million. However, our energy costs dramatically dropped in the long run. And so this is what I'm trying to demonstrate here is when you have a tool like the automated network sizing module, and you can go in here and have it size your pipes. It will automatically meet your design requirements. As you can see, all of our design requirements are met for velocity, pressure, and flow. Our pipe sizes now are between 14 inches and 24 inches in diameter. So we are dealing with larger pipe sizes, but the cost that you're going to be saving in the long run is dramatic. So here we only need about 74 feet ahead versus over 100 in the previous scenario. And so that energy cost savings is dramatic. And so that's what we have there. And what do you do if you are looking at this and saying, hey, that's great that I'm able to save all that money on energy costs, but my budget is $900,000. I can't exceed 900. I can't spend more money than that. What do you do? Well, one more scenario with initial cost budget. I only have to do one thing. I go back to the sizing panel, and if I have a initial budget that I have to stay below, that's what you do here. You turn on your initial cost limit, and let's say that this is $900,000. All right. So what I want to do is I still want to try and size my system for the overall life cycle cost, but keep the initial cost below $900,000. So this is where we might be able to get kind of the best of both worlds. So this could help us pay a little bit more upfront in initial cost, which is still not greater than our initial budget, but we can save a lot more in the long run. So let's run this scenario and see what we come up with here. So it's going through and it's doing the calculations. And the ANS module, this is literally going through millions of different combinations of pipe size. So it's going to be doing something way more effective than what anybody has time to do because of just how many different combinations of pipe size you can look at. All right, so it took here 20 seconds to do the simulation period. Bam. So look at that. We went from $4.05 million down to $3.5 million. So that's a significant savings, and we're basically right at our budget. So here, this goes to show where, hey, if you can allow spending a little bit more upfront, staying within your budget, this is how you can dramatically decrease your overall operating costs in the runtime or in the long run, and you can have much lower costs. So what impact is this going to have? Well, you're going to have your pumps be, your piping system is going to be sized exactly how it needs to be. You can then go and size your pumps based upon this operating point. That way, for this operating flow and pump head, you can find a pump that is very close to the best efficiency point, and that way it avoids several pump operating issues. And that way, one second, you're improving your pump efficiency, you're saving lots of money, and you're going to be having all those other benefits of improved reliability and runtime, a safer system, pumps that are not cavitating, and things are going to work a lot better. And that's going to be much, much better for the environment. So that's what I have for you today. Thank you all again very much for your time. I appreciate it. I appreciate you listening in. If you want to try out the ANS module, please feel free to contact me at benkeiser@aft.com, and I'll be happy to help set that up for you. And that way, you can try it out for yourself and take it for a test drive on your own. Thank you very much, everyone, and take care and have a wonderful rest of your day.